Number 68. Suppose you have a device that extracts energy from ocean breakers in direct proportion to their intensity. If the device produces 10 kilowatts of power on a day when the breakers are 1.2 meters high, how much will it produce when they are 0.6 meters high? All right, so basically you have waves that are breaking, right? So you have waves that are going to be at 1.2 meters high, and they're going to produce a power of 10 kilowatts, right? Now what's going to happen is when the breakers or the wave height is reduced to 0.6, we have to find out now how much will it produce, how much power, sorry, I'm like, wait. So we have to figure out now basically how much power, okay, it will produce when the wave is going to be half the height. So basically what we have to do is we're going to have to figure out, well, how does power essentially change in relation to wave height? And another way to talk about wave height is to call it the amplitude. All right, another way to talk about that is to just simply call it the x value. All right, the x value, right? The x represents you're used to thinking about that in terms of a spring, but it in terms of a general wave, because waves generate, because springs generate simple harmonic motion, and they can be described wave-like characteristics. So the x here is basic, or I should say the value is 1.2 meters and 0.6 meters is really our x value. So now what we have to do is we have to make the connection between power and essentially amplitude. So we know that power is simply equal to the energy per time, right? So the question now becomes, well, how is x, right, the height of a wave, how does x influence one of these two variables? Does it influence the time or does it influence the energy? And we know just probably by doing enough problems now that it influences the energy. Well, why? Well, you have the formula here, that potential energy. You can just call it energy in this case, all right? Because the energy in this formula is general anyway. It could be kinetic, it could be potential. Depends on what you're kind of talking about. So the energy here is equal to 1/2 force constant times the displacement, wave height, amplitude, whatever you want to call it, squared, okay? So I realize now that if I were to substitute that on into my formula now, right, for energy, I would have then the power is equal to 1/2 times k x squared all over t. Now the only thing that's changing between these two scenarios, right, is going to be the height of the wave and therefore the power, right? So what I can basically do is I can basically just find a simple fraction relationship. It depends on what you want to say and what you want to call it between the two. Meaning, I can do this. I can say that the power supplied when the wave is high, all right, should be equal to then 1/2 times k times the height of the wave squared divided by t. And now divide each of those by the power when the wave is low. All right, that would then be 1/2 times the force constant times the height of the wave when it's low squared, all divided by t. Now notice if I create a ratio like that, I can cancel these terms, right? And now I'm basically left with this, that the high power related to the low power will be simply equal to the height of the wave when it's high squared divided by the height of the wave when it's low squared. And now if I want to find, again, they're asking me basically what's the power when the wave is low, I can solve this for that, right? So I can basically have this simple equation now. So this will be the power when the wave is low will be equal to the power when the wave is high, multiplied then by the height of the low wave squared divided by the height of the high wave squared. And now we have to plug in. So this is 10. The answer I'll leave in kilowatts. This, since it's proportional, you don't have to change units, all right? But you can if you want, doesn't matter. So 10 kilowatts times then the low height, which is 0.6 meters squared, all divided by then the low height, low height divided by the high height, sorry guys, a little early, squared. And here we go. So this is 10 multiplied by 0.6 squared divided by 1.2 squared. And what do we get? 2.5, right? 2.5 watts. Okay. So basically, right, when a wave reduces by half, the power reduces by, it basically becomes 1/4, right, of the original. Now it's 2.5. And that's because the relationship has it's a squared relationship between the power and the height. All right, guys, thank you so much for tuning in. Appreciate it very much. Please remember to help us out and subscribe, and we look forward to helping you with more problems. Take care.